Elimination reactions is what we're going to talk about today. Yesterday, we just went over this homework. Of course, we talked about addition reactions. So we had a double bond, and we added stuff on to the double bond to make it single bonds. Today, we're going to do single bonds, and we're going to take stuff off and make a double bond. Okay, so it's basically it is the opposite of addition. Elimination is the opposite of addition. Okay. In an elimination reaction, atoms are removed from a saturated molecule, and a double bond is formed. It's the opposite of addition. A general elimination reaction looks something like this here, where you have a Y, something added on here, I don't know, whatever it is, we'll talk about that in a second, and Z here, and we're going to take those off, and then of course you're going to get Y and Z as a product over here, and what do you have left here is 2 free electrons, and that's where your double bond is going to go. Okay, so that's what we're going to be looking at today here. Alcohols are the first type that we're going to look at here. Alcohols, if we take off the OH part, of course, okay, they can be turned into alkenes when they are heated up in the presence of a strong acid catalyst. So one of the things that you want to look for is, if you remember yesterday with addition, we didn't have any catalysts yesterday. We didn't talk about H2SO4 or anything else that we're going to talk about today. So that's something to kind of keep in mind as well. That'll help you determine which type of reactions we're looking at here today. So this one here says we often need a strong acid catalyst like sulfuric acid. So propan-2-ol can be converted into propene. A water molecule is also produced. So here we see, this is the complete structural diagram, of course, of propan-2-ol. Okay, here's my CH3, my CH with my OH, propan-2, and then a CH3 here. This OH is going to come off, and this H beside it will come off. So these two things will make your water. Okay, and when that H and that OH come off next to each other, they have to be next to each other. You can't have it like 3 down the line, because what are you going to do with that electron over here and that electron over here? It's not feasible. Okay, so they have to be next to each other. The carbons have to be, and same thing. You can't take this H off here, for example, because if you took that H off and the OH underneath it, well, then you have 2 free electrons, but they're on the same carbon. That doesn't do anything about forming an extra bond. You have 2. In fact, that's pretty much impossible due to octet rule, et cetera, et cetera. So that's not going to help you either. It's got to be an H adjacent to it, for example. So that'll give you that there. And then what happens is you got your 2 free electrons here, and that's where your double bond will form. Okay? Now, some of you might be saying, how do I know which H to take off? And that is the question. How do you know which H to take off? Well, I'll tell you one thing. It's not the same. It's not this one here, because this is already got the OH here. You're not going to take that one off, because like I said, that would leave 2 electrons on the same carbon. So you could take off this one. You could take off this one if you want. You could take off this one, this one. Could you take off this one here? Does it have to be on that side? Could you take that one off? Sure you could. You could take this one off and this one off as well. And you might say, well, what if I take this one off? Does that change it? Well, in some molecules, yes, and in some molecules, no. Okay? In this molecule, if you don't know, well, if I took this one off, I'd get the double bond here, right? Is the double bond here the same as the double bond here in propene? Yes. So you just flip it around and you get the same structure, right? So no biggie there, or no piggy, yeah? Same thing, right? But yes, are you going to get some different options? Absolutely you could. So when we look at things like butan-2-ol, for example, that might give us different options. I don't know. Let's take a look. You'll see that this is not really written out that well here, guys, but down here I'll show you. Butan-2-ol, of course. Well, butan-2-ol, 4 carbons. This one has the OH group here. That's butan-2-ol. Let's fill in the rest with H's here. So 2 and 3. In the presence of a strong acid catalyst, that's what you would see there. Strong acid catalyst. Okay. Butan-2-ol, what's going to happen? Well, once again, the strong acid catalyst is going to help take off an H to go with this OH. So, where's the H going to come off of? Well, could come off of this one, and this OH is going to come off as well. So let's take a look at products here. Let me just move this up a bit here so I can have some more room. If the H comes off of there, I'm going to have CH2, double bond CH, CH2, CH3. Okay? The one other thing that you have to keep in mind is what are the other products. Sometimes we're really good at this, but we forget the little things. When you do an alcohol, when you turn it back into an, that alcohol into a double bond there, water, H came off of here, and OH came off of there, that is going to give me a water over here as a product, yes? So water is going to be a product, right? We'll talk about naming this one in a second here. Is there going to be another option for my hydrocarbon here when I take an H off? So the question becomes, well, how do I know I take this H off here? What if I took this H off of this one here instead? Is that going to give me a different product? And the answer is, could. Let's find out. If you're not sure, I guess you better draw it. CH3. CH is going to stay the same. This was CH2, now it becomes CH, and the double bond goes there. So I'm going to take an H off of here and the OH off of here. Okay? Yeah, I'm getting there. And then, of course, at the end here, CH3. Okay? But the double bond would now go on this side here. Okay? And then once again, if you're not sure, draw out all your possibilities and then say, okay, which ones are going to give me different names? Which ones are isomers of one another? Well, this is called, of course, but-1-ene. And this here, of course, is but-2-ene. Yes, in fact, those are different. And, of course, don't forget my other product is water here in this case. So those are my products for elimination of butane-2-ol. Okay? Good? Questions, anyone? Okay. So but-1-ene and but-2-ene are two options there. Okay? Good? Yes, moving on. All right. Butane-1-ol and sulfuric acid, for example. Why are we giving you this one here when we just did butane-2-ol? Well, let's see here. Butane-1-ol. And, like I said, sulfuric acid. So, once again, sulfuric acid there is to help speed up this reaction, help take off this H and the OH here. So what's going to happen as a result? Well, we're going to get, of course, that's butane-1-ol. I'm going to take this OH off, and I'm going to take off the H beside it. So CH now, and a CH2, and a CH3. Okay? So H comes off of here. OH comes off of there. Okay, those two come off. Of course, H and OH are going to give you water as well here. Do I have any other options for taking H's off in this one? Or is that my only option? That'll be your only option, yeah? So the reason we show you this one is because sometimes you're forced, there's only one product that's going to happen from this, of course with water, but in this case this would just be but-1-ene. Something to consider when you want to be specific about where you want that double bond. Now, if that double bond, if it happens at the beginning or the end, for example, obviously on the first carbon, it's a lot easier to kind of force it into that thing there, right? If the OH is somewhere in the middle, then you're going to probably have some options, right? Depending on which H you're going to take off. So that's the only products of this one, but-1-ene and water in this case, and that's an example of turning an alcohol into a double bond, an alkene, okay? So that's a little bit of elimination there. Let's look at the next one here. So alkyl halides can be converted into alkenes. Alkyl halides, so carbon chains with that halide. So fluoro, chloro, bromo, iodo, things like that, Frodo, Star Wars, can be converted into alkenes by reacting with a strong base, so such as potassium hydroxide, right? Bromoethane, for example, can be converted into ethene by reacting with potassium hydroxide. Here's how it happens, okay? Now, something important to remember, and we'll kind of do a little review at the end here once we're done all these reactions and stuff. But what basically happens with this, of course, water and potassium bromide products. When you see this kind of thing here, this is your strong base, of course. Strong bases could be a number of them, okay? So remember, bases have to have hydroxide, and a strong base is group 1 and 2 stuff, and usually you will see, you only really see 2 options usually, but there could be 3 or 4. There could be technically about 8 options, but usually it's a group 1 metal with a hydroxide. So things like lithium hydroxide, sodium hydroxide, potassium hydroxide, that's usually the 3 most common ones that you would see. So group 1, 2 hydroxides are strong bases. So you could use any of those, but I'm going to tell you, you're going to probably see lithium hydroxide, sodium hydroxide, or very, very often potassium hydroxide. Okay? The reason we have the potassium here, the potassium is there to take this off, the bromine. Always. The group 1 metal is always going to react with that group 17 halogen to take that off. That's its job. Okay? The hydroxide part, this OH minus part, is there for the H to take it off. And once again, it doesn't have to be that H. It could be adjacent H to it, of course. It can't be on the same carbon still, just like before. But the OH is there to make water, basically, with the H. Okay? Always, always. So when you do these ones, you'll always get a group 1, group 17 compound. Potassium bromide, lithium bromide, whatever, sodium chloride. You'll get some water, HOH. Okay? And then, of course, where those 2 were, you're going to get 2 free electrons here, and then, of course, that's where your double bond would go. Okay? Always, always. So, let's take a look at a few examples here. Isomers obviously can be produced by elimination reactions. We've already talked about that. You know, if the double bond can form at alternate locations. So, 2-bromobutane and potassium hydroxide. 2-bromobutane. Okay, butane, 2-bromo. And potassium hydroxide. Okay. Right away, you can say, okay, well, the potassium's there to take the bromide off. So I'm going to get some KBr. Or you could just write it all together, whatever, doesn't matter. And of course, if the Br comes off, I also need to take an H off so that I can form a double bond. So I will get some water as well, somewhere. Okay, from that. So those are 2 products quickly you can tell me that are going to form. Potassium is there to take the bromide off. Group 1 is there to take group 17 off. And the H is there to take an OH off. The question also becomes, of course, which H is coming off of here. So let's take this one off here. That's CH2, double bond CH, CH2, CH3. So I took this H off, okay, and formed the double bond between those, and of course the Br came off as well. So the double bond formed between those 2, okay. Or, does it matter if I take, because sometimes it will and sometimes it won't, it all depends. Does it matter if I take an H off of there instead? And the answer is it does in this case. You would get also CH3, CH, double bond CH, CH3 if an H came off of there. And of course, those are different compounds, right? This one here, of course, is butane, butanene. Had a lapse there for a second. And but-2-ene. Okay, so 2 different products, and yes, you still get your potassium bromide is what this is called up here. So potassium bromide and water are all your products. potassium bromide, water, but1-ene, and but2-ene. Okay? And that'd be an example of an alkyl halide. Okay? So basically a carbons, hydrocarbon chain with a bromide or a chloride or a fluoride or iodide attached to it. Okay? Okay, let's do the next one. I'll let you guys do this one here. Give you a little bit of time. Chlorocyclopentane and potassium hydroxide. What are we doing here? Chlorocyclopentane. Chlorocyclopentane. I'm going to put my chloro here. And what is it? Potassium hydroxide. So potassium hydroxide. What are my products? Strong acid catalyst. What are my products going to be? Well, let's see here. If we get the K's there to take the Cl off, so KCl will go together. Water will go together, of course. The OH is going to take an H off. So I guess my options are this one's going to come off, and that H there would come off. So I'm going to make, in that case there, a double bond there. All right. The question is, it doesn't matter if I take this H off or this H off, the one next to it. Is that not going to give me the same compound? Just over, right? So looks like we only have one product, well, with the potassium chloride and water, of course. But it's not going to matter if I take, you know, that off there, guys. You just flip it over. It's going to be the same, yes? So same thing there. This is cyclopentene. And I don't have to indicate where that double bond is, of course, because it's always on carbons 1 and 2, right? So cyclopentene. Yep.
It doesn't matter where you put it.
No. Okay. So that's elimination. Yes. Opposite of addition. Now we're going to talk about substitution. That's French. In a substitution reaction, a saturated hydrocarbon, so single bonded hydrocarbon, is going to react with a halogen like X2, for example, like Br2, Cl2, F2, etc., etc. All right. Now, here's the deal with substitution. These aren't magical names. These actually mean what they mean. Substitution implies that we substitute something on. Substitution means you put one in and you take one off, like in hockey or baseball or whatever. That's what we're going to do here. We're going to put in a halogen, like a chlorine or a bromine or an iodine or a fluorine. We're going to take off a hydrogen. And the question becomes, which hydrogen do we take off? And my answer to that is whatever one you would like to. Okay? So there could be, in this case, lots of options. A general, that's what it says underneath there, what you guys have, is a general substitution reaction looks kind of like this. So, for example, an X is going to come into, let's say, there, and that H is going to go there. Okay, we're going to substitute it in. Does it have to go to that one? No. It could go to that one, and that one could come off and go there. So we could end up with more than one type of product, of course. These reactions tend to be very, very slow, substitution. This is not like addition where you just add stuff in and it happens very quickly. So, you know, if you're doing this with the bromine, for example, that orange color may disappear, but it's going to take a long time. To help speed up substitution reactions, we use the source of UV light, ultraviolet light. Okay? That is your catalyst in this particular reaction. So when you see UV light, in the presence of UV light or ultraviolet light, you probably will have a pretty good idea that that's substitution, because that's the only one that uses it. Okay? Substitution reactions are very slow, have very slow reaction rates. The reaction rate can be increased by using ultraviolet light. All right? So let's take a look at our first one here. Propane and bromine with UV light here. Propane, propane and bromine with some UV light here. Okay? So, once again, what's your options? You're going to put a bromine into one spot. You're going to take a hydrogen off from that spot. So, I'm going to take a hydrogen off of here and put a bromine on. And of course, this will stay the same. All right. So I decided to take my hydrogen off this one first. But who's to say it's that hydrogen, one of those ones? It doesn't matter which hydrogen you take off of that first carbon. No. Okay, it's going to be on the first carbon, right? What happens if I took, I don't want to take it off of there. I want to take it off of this one. So is that going to give me something different? CH3, CH with a Br, and a CH3. Is that going to be something different? Yeah, I think so. Okay. What if I don't want to take it off that one? What if I want to take it, oh, sorry. I wrecked that there, CH3. Okay, what if I wanted to take it off? What if I take the hydrogen off the last one instead? So I don't want that. Now I want this one here. So CH3, CH2, CH2Br. Is that different than the other two? That's the same as the first one, right? So I don't need that one, obviously. We're not going to write it. That's silly. Okay? So I don't need that one. What else do I get? Well, don't forget, where's that H going? The H comes off of here, and it goes to there. That Br is going to there, for example. So the other product that you get here is hydrogen bromide. Okay? And of course, you'll have to name these. So this is 1 bromo propane. Is that what we're doing? Sure. Propane. And 2 bromo propane and hydrogen bromide. Okay? So, those are your 3 products there in that case. Good? Yeah? That's substitution. Now, longer chain, you get more options, right? So these could quickly get out of hand here, and we could have, 5, 6 products perhaps in some cases. So here we go. Iodobenzene and iodine. Iodobenzene and iodine. Well, okay, so iodobenzene and iodine. Remember, benzene special, it's C6H6 normally. In this case here, we have an I instead of an H there, so that's fine. There's no H here to take off, basically, is what I'm saying. So there's no H there to take off because it's C6H6. However, the I is going to come in, the I is going to come in, and the H is going to come off, right? One of the products I'll just write down here right away is going to be HI, which is, of course, hydrogen iodide. So don't forget about those little things like that. That's important. Hydrogen iodide is a product. Now, what are the other options? I goes in, H comes off. So here we go. There's my original I. I'm going to put an I on there. Okay. H came off of that one. I goes on to that one. What about I was there? What if the I goes there and takes off that H instead? Is that something different? Yep. So, rolling along here. What if I was here? What if the I comes off of this one? Is that something different? Yep. What if I do the next one here? No? Okay, so the next one is going to be a mirror image of this one, yes? When I put the I coming out here, instead of there, it's going to be the same, yes? And then the next one's going to be the same again. So there's your options. 4 products, those 3, and of course hydrogen iodide. This is 1,2-diiodobenzene. This is 1,3-diiodobenzene. And this is 1,4-diiodobenzene. Okay? So there's your, well, 3 hydrocarbons and your HI, of course. Okay, good? Yep. Woohoo. So that's substitution. All right. Esterification. We've done esterification already. I've kind of taken some time with this, so this is going to go probably fairly quickly here. An ester, of course, is produced. Ester is, of course, esterification reaction. It's produced by the reaction of an alcohol and a carboxylic acid. Water is also produced in these ones here. Your general equation, it says these slow reactions are typically require a catalyst again, so usually in the presence of a sulfuric acid, a strong acid. This is your typical kind of carboxylic acid alcohol to give you an ester. So remember, first of all, the OH comes off the carboxylic acid here, and this H come off to give you your water, of course. The H comes off the alcohol. Right? We've talked about this before, so this shouldn't be anything new to you, and if it is, you should pay closer attention perhaps. R is, of course, the chains that are attached to either end there. And then remember, when those things come off, you just squeeze it back together again. So it's that squeeze play I talked about, Price is Right, Bob Barker, right? That stuff, if you just kind of lifted that out and squeezed it back together, this part here, of course, was your carboxylic acid. That's important to know. That came from the carboxylic acid. This part here comes from the alcohol, if I can spell it. Alcohol. Well, that's not L. Alcohol. Okay? Comes from the alcohol. Okay? And then, of course, once again, you get water as a product. That H and OH combined together. So, let's take a look. Propanoic acid and ethanol. Propanoic acid and ethanol. Propanoic acid, I like to do them like that all the time because it kind of helps me keep it straight, because I always know that I kind of name them the same way all the time. That's not always going to work out for you, but if you can do it, that's fine. 2 and 3. That's propanoic acid, and I forgot now, ethanol. Ethanol is, of course, let's see, CH2, CH3 with an OH group coming off there. Ethanol. In the presence of a strong acid catalyst, that will give you, well, once again, you have to keep it, you have to remember, it's very important to remember which OH and which H come off. So it's this OH that comes off and this H that comes off. Those two come off and you're going to get water as a product. Then what I like to do is, if you write them out like that, it's nice and easy because they're usually together. Right? Try and write the OH close together like that. Those come off and then you're left with CH3, CH2, C double bond O. That's gone. Now we're hooking it to this O here and CH2, CH3. And of course this is now an ester with a carboxyl group in the middle. And I would call this, remember, this came from the alcohol. That comes first. That's called ethanol, turns into ethyl space. Right? So ethyl space, and then we got to worry about the other side. And of course this was propanoic acid. We don't call it propanoic acid anymore because we call it propanoate. Propanoate. All right? So ethyl propanoate in this case and water are your two products. And I guess I should probably put a little plus sign there. Okay? So, ester is, of course, made up of two parts. Part coming from the alcohol. This is your alcohol part, by the way, right here. Once again, that's your alcohol part. That was ethanol, becomes ethyl. This is your part from the carboxylic acid. In this case, it was propanoic acid. That turns into propanoate. And these can get quite complex, of course. And I guess we're going to find out who really understands this shortly here. Yes? The next question there, you guys can go ahead and start reading there. I don't know, look it up. All right? All right. That should be enough time for you here. First of all, when you see this, you want to make the production of pentyl propanoate. We know this is an ester, of course. This was your alcohol part. This was your carboxylic acid part there. Now, fine, good, sure. You may want to start by drawing this out, actually. To draw this out, pentyl propanoate would look something like, I'm going to leave this maybe arrow there. Pentyl propanoate looks like, let me do this, C double bond O. Propanoate was your carboxylic acid, so I usually like to put that over on this side here, 2 there. That was your propanoate, which came from propanoic acid, of course, no shocker there. And pentyl. Well, pentyl is your alcohol part, which is CH2, 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 and CH3. Okay? That is pentyl propanoate. Now, remember, once again, this part was your carboxylic acid. So if I had propanoate, that had to come from, of course, this kind of looking thing here, where the OH would go back on to that carboxylic acid there. This is called, and you'll have to name these, propanoic acid, of course. And to make the alcohol, I have pentyl. Well, I'd have to put the H back on this one, and CH2, 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 CH3. That, of course, is, well, 5 carbons. That is pentane 1-ol. So don't forget the number there that goes with that. It's not just pentanol. It's pentane 1-ol. Now, you could most certainly make different types of structures. You know, for example, we could do pentane 2-ol. We could do pentane 3-ol. How would that look differently? Well, that can get kind of confusing, right? Because you need to attach it where the O is, because that H is the one that's coming off. So if we had the OH moved over here a little bit, well, then you start getting methyl groups added onto that as well, right? And because maybe not pentanoate right away, it could become, because those 5 carbons were all in a row, sure. Now it becomes perhaps butanoate, or sorry, butyl, instead of pentyl. Or we could even cut it down further. We might even be able to make an ethyl out of that, or a propyl, I should say, with an ethyl group added on. So it can become quite confusing. If the alcohol group's not at the end, then you got to be very careful how you're going to join that together. It can get confusing, because if we move this over, remember, it's this H that's coming off of here. What if that H is not at the end there, the OH is not at the end? What if it was over here? Well, then you're getting this added on with that little bit of added on to that added on thing. It becomes 1-methyl butyl now, or 2-ethyl propyl is an option, etc., etc. Fun is what I call it, actually. So, good? So, that's what that one looks like there, and I believe that's all we have for you there. Good? Now, before we're done here, real quick. So, we've looked at 5 reaction types. First of all, we'll talk about combustion. It's the easiest one. Combustion is plus O2. Okay, that's just CO2 and water. No biggie there. We talked about addition. What do you need for addition, guys? Addition. What are you looking for?
Non-saturated hydrocarbon and hydrogen, like actually molecule.
Sure. Yes. Yes. So you're looking for basically, in English now, double bonds or triple bonds, yes, right? And you're going to add stuff into that, whatever that happens to be. So you need to start with the double bond, right? Have to. Do you have any catalysts for addition? No, just add it on, right? So there's no H2SO4 or anything like that. Then we talked about elimination. What do you need to start with elimination? You need to have saturated, so single bonds in English, yes? Starting with single bonds, and you got either a strong acid catalyst to take off H and OH. So if you see an alcohol with H2SO4 and it's all single bonds, and it will be, you'd be like, oh, that's probably going to be elimination. Or if you see a strong base with a bromide or a chloride or a fluoride or an iodide, you think, hey, that strong base there is to take off the that bromide or iodide or chloride, that halide, and an H as well, of course, with the hydroxide part. That's elimination. Okay, so strong acid catalyst, strong base, reactor with a strong base are options. And then, of course, we did a substitution. Substitution, you need once again, single bonds. You can't do substitution with a double bond, right? Because then it's addition. We've discussed that already. So substitution has to be single bonds. You're going to put something on, you're going to take something off. You'll see UV light. Okay, those are all things that you need to kind of cue into. Maybe make cue cards again for those to kind of help you remember those. All right. Esterification is the last one. It's probably, you should recognize that one, hopefully. It's going to be an ester, so a propanoate kind of thing, or a butanoate. It's an ester made from a carboxylic acid and an alcohol. Okay, so you have to know that that's the reaction takes place there. So there's 5 reactions. They're kind of, you know, if you kind of understand what we just talked about in the last 2 minutes, you'll be okay, because that's pretty much it, right? I mean, there's only 2 single bonds that are involved, and that is, of course, substitution and elimination. So if you can kind of figure out what the difference between those 2 are, you're probably set, okay, for the most part, I would say. But once again, you need practice with that, and we got a worksheet for that. So, okay.